The topic that we're going to be focusing on from this week's module is circular motion. In particular, we're going to be looking at how circular motion is used in the construction of streets and highways. Streets are constructed with ideally banked curves, in which the road is angled downwards, with the lower side being closer to the inside of the turn. These banked curves are used so that one can make the curve at a certain speed without the aid of friction. Therefore, the turn can be made safely without the car sliding out. If a car is on a level, unbanked curve, the forces on the car are its weight, mass times gravity, pulling the car downward, and the normal force, N, which pushes the car upward. Both of these forces act in the vertical direction and have no horizontal component. If there is no friction, there is no force that can supply the centripetal force required to make the car move in a circular path, meaning the car cannot turn. On the other hand, if the car is on a banked turn, the normal force, which is always perpendicular to the road's surface, is no longer vertical. The normal force now has a horizontal component, and this component can act as a centripetal force on the car. The car will have to move at the correct speed, so that it needs a centripetal force equal to this available force. This is one of the reasons why speed limits are enforced, as to protect the safety of the cars. Given the right speed, a car can negotiate a banked curve even if it is covered with perfectly smooth ice. The equation for finding the angle needed for a car to make a turn at a certain speed is net force is equal to the centripetal force, or mg tangent theta is equal to mv squared over r. R is equal to the radius of the turn, v is equal to the velocity of the car, g is equal to the freefall acceleration of gravity, or 9.8 meters per second squared, and theta is equal to the bank angle of the curve. Let's look at an example. A turn of 100 meters is being designed for a speed of 25 meters per second. At what angle should the turn be banked? So we know r is equal to 100 meters, v is equal to 25 meters per second, and g is equal to 9.8 meters per second squared, and we're solving for theta, the angle of the curve. Let's look at our equation. First, we can cancel out m from both sides and divide g on both sides, leaving us with tangent theta is equal to v squared over r times g. So theta is equal to the inverse tangent of v squared over r times g. If we plug in our numbers and solve, we get 33 degrees. Therefore, for a curve with radius 100 meters at a speed of 25 meters per second, the bank angle should be 33 degrees.